Well, hello class, welcome to section 4.2. So we're going to try and do the same things we did with functions in one variable, as in find the derivative, find the instantaneous rate of change in a function, find slopes of tangent lines, all for the purpose really, as we had seen in chapter 2, of finding minimums and maximums of functions, right? So there's a maximum, there's a minimum. We saw that those important points occur when the derivative is equal to 0 and it's undefined. So the first task at hand is to learn how to take a derivative of a function of several variables. So these are called partial derivatives. So partial derivatives is what we call derivatives of functions of several variables. Because as it so happens, we are not taking just one derivative, but we are taking several derivatives. Okay, so here's a picture. And here's a point. Here's the picture that we actually went over in 4.1, describing to you what the graph of a function in two variables would look like. So you need an x and a y input, and then that point of coordinates x comma y creates one output once plugged into the function, and the output is a number, right? So really you get a three-dimensional picture here because you need the x dimension, the y, and they produce the z dimension. Good. So look at this point right here. Now, if I were to go down this way towards x, as you see, the function seems to be where the curve or the surface seems to be dropping, yes? Whereas if I'm moving in the y direction, this surface seems to be, well, maybe a little bit even or going up. But definitely what this shows us is that from any point, it really matters in which direction we are moving. So that's why we call these partial derivatives. So what we're going to simply be doing is for any function of two variables, we're going to have to take two derivatives, one in the y direction and one in the x direction. So as you see here, this is a derivative exactly in the parallel to the y-axis, to the x-axis. So that's what we call an x direction. Whereas this tangent line here goes in the y direction, so it's parallel to the y-axis. So df, that's how we would read this, df dy, even though I'm putting a different symbol than we used in chapter 1, I still call it a D. It's a Greek letter D. Well, kind of. I don't even know what letter that is, but there it is. So what this simply means is the change in the function f with respect to a change in y. And the same way, we have a change in the function f with respect to a change in x. That's what these things mean. Okay, so partial derivatives definitely are slopes. They are derivatives, yes. So a derivative is a slope. It's just that it's a slope in a different direction. Okay, so to find these partial derivatives, we only change one variable at a time. Okay, so what does that mean, that we change only one variable at a time? All right, here it is, the partial derivative of a function with respect to x. It's the change with respect to x, as you see. So look, I'm bringing back, now that we're going to be using it, so don't freak out. Now that we'll start using the limit definition, but when you think about the limit definition, this is what it's happening. So as you see, who am I changing slightly? the x value. The y value stayed the same, yes? So as you see, it's in change with respect to the function as we change x by just a little bit much. The y value doesn't change. So the same way, if you look at the partial derivative with respect to y, who am I changing here? Just the y value, right? Gets increased a little bit by a tiny h, right? Remember our derivative definition that we just see to find an instantaneous rate of change. All we're doing is just moving a tiny little bit, right, from an x to an x plus h. And then we see what happens to the function value on this tiny, tiny interval, right? And we let it get close to 0, that h. We said that's why we're finding this limit, yes? So we change one thing at a time. So just as I had said before, partial derivative simply means that we are changing one variable at a time. So just to be clear, a function of two variables will have how many partial derivatives? What? We'll have two partial derivatives, yes? One in the x direction and one in the y direction. Okay, now sure enough, a function of three variables will have three partial derivatives, and so on and so on. So that's what I was actually saying last time, that we are in section 4.1, that we are going to mostly deal with functions of two variables only, because things will get crazy really fast with more variables, right? A function that depends on more variables. There's going to be quite a lot of computation just to find the derivative. Don't even get me started with the second derivative. That's coming up in 4.3. And I'm guessing you might be guessing what's going to happen when you want to find the second derivative for these two partial derivatives. So yes, it does grow exponentially. Okay, so therefore it said the partial derivative with respect to x is just a regular, right, derivative with respect to x with y held constant. That is so important that you are keeping y constant, so it acts just like the number 2 that you might have in a function, or just like the number 5, you'll see. And so the same thing, the derivative with respect to y is you take the derivative with y being your variable and x being held constant. So nothing is happening to, so just to bring this back, when you take a derivative with respect to x, see how y is staying constant? It hasn't changed at all, yes? And then the same thing here, if you take a derivative with respect to y, the x values don't change one bit, right? They stay constant. Okay, so let's see how that would work when we take derivatives. It's just see what happens. So I'm starting with a pretty simple function right here. As you see, the x's and the y's are a little bit separate from each other. Let's take the derivatives, right? Remember, there's two of them. So df dy, oh, maybe we need, oh yes, I do have a notation right here. So again, we're not using the letter D, but more like this delta Greek letter here. Just to make the difference between a regular derivative, an ordinary derivative, and a partial derivative. But either way, this is the better notation. We can't use prime because, well, we need to say who we're taking the derivative with respect with. And a better notation is that we put this little x subscript when we take the derivative with respect to x. So we don't really want to write d dx. That's a lot to write. Well, not that much. But even faster is simply to write fx. Okay, subscript x. Okay, so what is the derivative with respect to x? Well, again, remember, y is a constant. It acts just like the number 9, but x is your variable. So the derivative of 4x squared is 8x. This is a constant, right? There's no x in it. So this is going to go to 0, and this is going to go to 0. And that's it. That's your answer. And the derivative with respect to y, pretty much the same. There is no y in this term, so as far as y is concerned, this is a constant, so the derivative of 4x squared is 0. The derivative of negative 3 times y is negative 3, right, times 1. And then 9 is a constant again. It has no y in it, so that goes to 0. So that's just how simple this is. Okay, so remember, you deal with one variable at a time. So let's try this one. The derivative with respect to x. Now remember the e function. So the derivative of e to the 2x is e to the 2x times, move on into the exponent and take the derivative of 2x, and you're going to get a 2. Okay? If you want to write it prettier, you put the 2 at the front. Okay. Now, why did I stop? Of course, because is there an x in this term? No, there isn't. So this is constant. It's not changing at all. It goes to 0. Okay. The derivative with respect to y, fy, the same way. There is no y value in here, so that derivative is 0. Minus, we keep the coefficient, the derivative of 3 times y, natural log of 3y is 1 over 3y, times, move on the inside and take the derivative of 3y, and the derivative of 3y is just the 3. So reducing these will get us negative 1 over y. There's your answer. Okay, so now in this next example, I'm starting to mix up a little bit the x's and the y's in the same term. So see if we can keep this straight. Okay, what is the derivative of 3xy? Remember, y is a constant. So it acts just like any other coefficient. So it's as if y is 10. So if y is 10, you'll have a 30x, and then the derivative of 30x will just be x. If y is 100, you really have a 300 here, 300x. So the derivative of 300x is just an x. Now, basically what I'm saying is that what x is multiplied to is the coefficient 3y. So the derivative of 3xy with respect to x is just whatever x is multiplied to, which is 3y, minus the derivative of this, we already know, is 12x squared, right? It stays the same. Is there an x in this term? No, there isn't. So the derivative of this term goes to 0, plus, what's the derivative of x squared, y squared? Well, the derivative of x, again, y squared is a coefficient, so it stays, yes? Times, it's like the number 5. So 5 times the derivative of the x squared part is just 2x. So that's pretty neat. Again, all you're doing is just concentrating on the variable x. That's your variable. And if it's multiplied to a 5 or a y or a 20, it really doesn't matter. That just stays as a coefficient. So if you want to make it a little prettier, I didn't leave myself room, but that's a 3y minus 12x squared. What I mean by prettier is to put the 2x at the front of y squared. Okay, so let's try fy. Okay, so what is the derivative of this function with respect to y? 3xy, again, y is multiplied to 3x. That's its coefficient. So the derivative of that is 3x. That stays, times the derivative of y is 1. There is no y in here, so the derivative of 4x cubed goes to 0. Plus, the derivative of this with respect to y is 42y to the 6, plus the derivative of this, the x squared stays, and then the derivative of y squared is 2y. So just to not have to write it again, I just wrap the 2 in the front. There it is. Okay, all right, let's try the next one. So, what is the derivative of e to the xy? Well, we have two choices, fx and then fy. Okay, so fx. The derivative of any natural exponential function, first of all, has to stay the same, right? So the derivative of e to the anything, well, unless it's a constant, right? There's no variable in it, then it's going to go to 0. But the derivative of e to the xy is e to the xy times. Move on to the exponent and take the derivative of the exponent. So the derivative of x times something is just that something. So it's a y, right? So it's a 1 times y. Now, the derivative with respect to y and the same, it's really the same. By the way, I'm going to say something in a minute. So it's an e to the xy times, move on to the exponent and take the derivative of xy with respect to y. So it's an x times 1, which is just an x. We call, these are basically symmetrical to each other. So see, if you swap x and y, you get the same thing. So the derivative with respect to x would be the same as the derivative with respect to y, just by swapping x and y. So instead of a y, you have an x. So it's just x and y are interchangeable, and so will be their derivatives, right? You just have to interchange x's for y's. So there's another one like this. Let's see if it works out the same way. So what's the derivative? Well, first of all, before I even find that derivative, what would be a good idea? Sure enough, as always, we need to rewrite that square root as a 1/2 exponent. And you know you're not allowed to square root each one of them. The radicals do not get distributed to sums and differences. Okay, all right. So what would this be? Okay. Right, yes, fx. The derivative of this is going to be a chain rule. So the first thing I'm taking care of is the outside exponent. So